Hello, my name is Antonio Gonzales, and right now we're going to look at sodium bicarbonate. So although you might not know it by this name, it's almost guaranteed that you have encountered sodium bicarbonate. Sodium bicarbonate has many applications that you'll see in greater detail later in this video, but to summarize quickly, it is commonly used in the human drug field as a blood pH buffer. It is also seen as a quick and easy cleaner/deodorizer in the home place, like in my family where it seemed like there was always a little orange box of sodium bicarbonate in the fridge to tame the smell. That little orange box brings me to the reason that most people probably know sodium bicarbonate. Baking soda. Baking soda has been a household staple in part because of its extensive uses. For me, baking soda has always been synonymous with, well, baking. One of the most popular use cases is as a chemical leavening agent in all kinds of baked goods. These are some of sodium bicarbonate's most impactful applications, and while it does have many more, time is better spent looking into why it has so many. That why starts with how sodium bicarbonate is produced. Sodium bicarbonate is produced with NaCl and calcium carbonate reacting with other intermediates within the solvay process. This calcium carbonate can either be extracted from limestone deposits called trona or can be synthetically produced, in which case it is called precipitated calcium carbonate or PCC. To start, calcium carbonate is first decomposed. This process is endothermic and requires an input of energy. One product, carbon dioxide, is used in the main reaction between aqueous NaCl and CO2 in the presence of ammonia. This reaction yields ammonia chloride as well as sodium bicarbonate. Now I know what you're thinking. Well, geez, that's a lot of manufacturing processes for an organic compound, right? To which I would say, actually, that's a lot of processes for an inorganic compound. Let's take a look at sodium bicarbonate. This is the Lewis structure. As the name implies, sodium bicarbonate is the sodium salt of the bicarbonate ion. It looks like something you would see in your organic chemistry class, but actually, carbonates are one of the few carbon-containing molecules that are classified as inorganic molecules. This classification may come from, in part, the compound's lack of carbon-carbon and carbon-hydrogen bonds that are typically seen in organic molecules. Now, just because sodium bicarbonate is classified as inorganic does not mean the principles of organic chemistry do not apply. The key part of the sodium bicarbonate is the bicarbonate ion. The ion is the conjugate base of carbonic acid. Carbonic acid is considered on the weaker side of acids with a debated pKa of around 3.45. This means that the carbonate ion is basic with a pH of 1% solution of about 8.3. The bicarbonate ion has a negative charge resulting from the deprotonation of carbonic acid, leaving an oxygen with a formal charge of -1. But because of the nature of the CO sigma bonds in the 1CO pi bond, this molecule can be stabilized via resonance. Along with providing a basis for resonance stabilization, those CO bonds also give rise to highly polarized covalent bonds. The oxygen atom has a higher electronegativity value resulting from its higher effective nuclear charge and will attract the electrons in the CO bond more strongly towards its own nucleus. This will leave the oxygen with a partial negative charge and the carbon with a partial positive charge. Again, I know what you're thinking. Oh geez, that's a lot of charges. But just hold on, because there's more. Now you may have noticed that there's still a hydrogen bonded to one of those oxygens, and that introduces more charges. In a similar vein to the CO bond, the oxygen is more electronegative than hydrogen, contributing to more partial negative charge on the oxygen and a partial positive charge on the hydrogen. What's the culmination of all these charges? Sodium bicarbonate can interact in a lot of ways with polar solvents like water. The sodium salt ion nature means that it will be soluble in polar solvents like water with roughly 9.5% solubility at 77 degrees Fahrenheit. Also, all those partial charges are able to interact via dipole-dipole IMS with other polar molecules, and specifically those oxygens and hydrogens are able to H-bond with other bicarbonate ions and water. All those interactions give rise to reactions. So how does sodium bicarbonate react? Sodium bicarbonate will dissolve in water, but will not react with water in any meaningful way on its own. If you look at the mechanisms, it could react as a base with water as an acid, where the electrostatic attraction from the oxygen's lone pairs and the partially charged hydrogen of the water would lead to reaction. But this will not occur because the resulting products are stronger acids and bases that will push the equilibrium to favor the reactants. It could also react as an acid, with water as a base, but will not because the pKa of the bicarbonate ion is around 10.32, making it a very weak acid. The products of this mechanism will once again be stronger acids and bases that would push the reaction equilibrium to favor the reactants. Sodium bicarbonate needs to be in the presence of water and an acid to make a meaningful reaction, because it will not react in its solid state, which is why the water needs to be present. When reacting with a generic acid, the basic bicarbonate ion will be protonated due to the electrostatic attractions mentioned earlier, resulting in a carbonic acid and a generic conjugate base. The carbonic acid will then decompose into carbon dioxide and water in only a matter of 300 nanoseconds. This acid-base reaction resulting in some pretty harmless and neutral products of water and carbon dioxide is why sodium bicarbonate is able to be used in the ways mentioned at the start of this video. The neutralization of acid is what allows it to be a good blood pH buffer, along with the other H being able to protonate hydroxide ions if the blood becomes too basic, which leads to its common use as a treatment into ailments like metabolic acidosis and acid reflux. This also allows for its use as a deodorizer, as it neutralizes the fatty acids that are usually associated with bad smells. The reaction of baking soda can cause dirt and grease to be more readily dissolved in water, which allows for its use as a cleaner. And finally, its use as a chemical leavener results from the CO2 bubbles creating pockets of gas within the crumb structure of baked goods, giving them rise in oven spring. Now that everything's come full circle, I hope that this video was informational and educational about sodium bicarbonate.